James Sylvester from JPS Reliability and the Reliability Training Institute RMS. What we're going to go through today is a bonus case study 6, which is dynamic vibration absorbers, distributing energy in line with the first law of thermodynamics. This is a slight change from our first 5, and this one actually does probably go on a lot longer, but we really thought it would be great to show you how we can find a defect, work out what's going on, and resolve it. The previous 5 case studies, if you haven't seen them, they're available on the RMS website and also on my blog. On these case studies here, for example, number 1 was an electrical motor terminal defect connection found through vibration analysis. In this case study, we also showed that using thermal imaging would also, an additional tool, would have resolved the defect quicker. Case study 2 was a standby fan motor defect. This one was transfer of vibration from the surrounding areas, and it highlights the importance of rotating standby units. Case study 3 was a variable frequency drive defect. In this instance, the vibration analysis was an indicator that we had an issue with the system, and we resolved the issue. Case study 4, a screen gearbox. This was great to show that using the correct measurement parameters, you can resolve near enough anything with vibration analysis. And case study 5, the last one last week, was on the 4-point contact slow rotating bearing. Now, all these case studies are real life case studies from real data. They're all from my book, which is Enhancing System Reliability Through Maintenance Technology. Chapters 1 and 2 is on mechanics of failure and condition monitoring. That's what we've worked on with Doctor at the American Science, and that's where we bring the science and reality together, talking about the functionality of a system. So that as a whole system can actually function to do a job. And also we talk about the predictors and the indicators of each defect. Now each technology can it's all interlinked. Now we'll get into case study 6. So the background on this one was, it's a pumping station, and as usual, we only got involved when they had repeat failures and they keep trying to fix it, and when they couldn't fix it anymore, they thought they'd give us a call. So we came along and we looked in. These are large motors, 5,000 kilogram, about 3 meters high and about 1 meter and a bit square. Sleeve bearings. At the top is a tilting pad thrust bearing and a radial tilting pad bearing, and it's a tilting pad radial bearing at the bottom, and it's got a 6 meter cardan shaft down to a pump. They've been having random routine failures of these pumps. Lots of people come along to try and fix it. One thing we did see was that there wasn't enough record keeping of the failures, and when a failure happened, it is a panic to get it back up and running, so no one revisited it. Once it's fixed and it's running, forgot about it, onto the next problem. The documentation of previous failures was limited. Everyone, the fitters, the mechanics, electricians, process, all had their own opinions of what was causing the failure to add more confusion. Previous experts have been in doing non-standard tests, like in the MCCs, and calling misalignment as the issue when they're not actually looking at the system and could see it's a cardan and shaft. So various attempts have been to resolve it. So when we got involved, we had a look at the first failure we got involved with. So this failure here, so if you look under here, this is the bed plate underneath. This has been dropped down from up on the motor, and you can take a gasket down, and then the tilting pads will come down. So we dropped the oil out and then had a look at the oil. And what was quite shocking, we could see shards of babbit material in the bearing in the oil. So straight away, we knew the bearing had obviously failed. I took out all the bearing elements and cleaned them up. And surprisingly, it went from a stage of an absolutely perfectly non-used bearing to a little bit of wiping, more wiping, all the way through to high wiping and actually a cracked tilting pad. So when we looked at that, we thought, well, that means the shaft itself isn't running concentric, the non-orbital motion. So something's causing that shaft to rub and load up and not move in a nice circular motion at the bearings. And it's always the drive end bearing that failed. Here you can see the good pad, no wiping, still the machine marks. And on this one here, you can see heavy wiping. When we actually looked at the crack pad, what was interesting, you see these little cracks here. It's peeling as if it was coming up, either through subsurface fatigue or the babbitt to base materials coming up. So we turned it on the side and we can actually see the bond line was absolutely perfect. Nothing wrong with the bond line. And these little craters here was where the babbitt material was coming up. And coincidentally, it actually broke right on the pivot point at the middle. So with the tilt and pad remove, the shaft is being non-eccentric motion, loading it as bearing, and it's cracked. Talking to operations, and they said it's always the drive end bearing that fails. There's a rank of 4 of these pumps, and they're sort of all failing, and they're chasing around, repairing them, getting up and running, and they're failing, and they're trying to work out what's going on. So what we did, we went to site, and on the ones which were running, we carried out a vibration analysis survey. And what was quite actually stood out a lot was high directional vibration. So here you can see horizontal, vertical. So we're talking radial at the top, so that's 90 degrees apart. Huge directional vibration, all at one order. Now these pumps run on the set dial from 0 through to 5, so 6 set points, and they all had a slight different characteristics, but every one, as you increase speed, the vibration got better. So with high directional motion, speed related, force and function one order, the first thing that springs to mind is some sort of resonance. So with a resonance, we can either stiffen it, like on a guitar, if you stiffen up the strings, the pitch goes higher, so you can stiffen something to increase the resonant frequency, add mass to lower the resonant frequency, and also you can use damping or stiffening to dampen the resonant frequency. And the easiest one of all is change the forcing function, but unfortunately with this one here, you can't change the forcing function. So the first thing we do is try and prove that it was a resonance before we looked into what kind of resonance it was. And the easiest way to do that was to add mass to the motor. So here you can see we slung over the eyes some massive crane weight, bit of board, strapped it. And on this particular one, it actually changed. So on this one where we had a high peak at set point 3, we put the weights on and then lowered it to set point 2. So straight away you think, yep, there's a resonance issue in here. Pretty confident we got a resonance issue. So we had 10 kilogram weights around there. This is a trend. So here you can see the speed going up. So as the speed goes up, the vibration increased and then it came down. Whereas before on this particular pump, it is actually higher speed, set point 3. So this type of relationship with the speed and the vibration, and the fact that we added a mass and it changes it, speed changes it, it is a resonance frequency. It's not misalignment like people have been saying, it's caused by a resonance, but what is causing this to have the resonance problem? We looked at the data another way. So here on a similar pump, we have set point 3 and set point 5. So on set point 3, you can see, if you imagine this coming up, it's all going bum, 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 like this. So that motor there, when it's running at set point 3, highly directional, is juddering and a motion coming around. Yeah, you put up to set point 5 and it's a lot smoother. So down here, you can see it's a lot more smoother motion. So we're getting this data up to try and show, to explain to the asset owner that the problem is resonance. Orbital data. So here is non-filtered. You can see it squeezed in and pushed out. we filtered it for the run speed at this one, which is 704. Perfectly orbital shape. So that pump was moving hugely directional. And by the trace, we know it's juddering as it's doing it. So it's giving a bit of wobble out. The top end of the motor is doing this. So the next test was a bump test. So here we came down onto the bed plate, put a transducer down there, pump was off, neighboring pumps were off, and we did the bump test. And we actually had two resonant peaks at 537 and 650, but a whole broad range where it raised up twice. Sod's law, this here is at running speed. So we're running here with the set points, which shows that we're running on a cusp of resonance. And we bumped the bed, so we got a structural resonance problem. Now, you might think, why didn't you feel that? Well, here is a forced floor. So all around the pump, it's got RSJs with a forced checker plate floor. So when you're stood at the pump, you can't feel nothing for your feet. So they're going, well, how can it be the structure? Because it feels solid. But there's like a 12-inch air gap. This under here is a structure. So we took up there, and you can actually see the pump structure there. And underneath the bed plate, it was here. Now, next thing was to say, we have to eliminate any rotor issues or any rotor problems. So the pump which failed was back in the shop. So we went to the workshop where they were repairers that were repairing the pump, and we did a coast up amplitude and phase plot. So that's basically, we put the transducer at the top of the motor where we knew we had the highest flex on site, tacho tape to the analyzer, and did amplitude and phase. And yes, there is two rotor criticals here. So you can see as it phase goes for 180 degrees, we got one high peak, and here where it goes for 180 again, we get another high peak. But this is down at 300 and 375 RPM. The actual run speed on site, that motor was running super smooth. So we confidently say to them, there's a resonance issue. It's nothing to do with the motor. The motor is a force, but it's causing the bed plate to move, which is causing your motor to twist like this. So this motor went back on site. So we did a follow-up test. And here we have these low range 180-degree changes. But look at this here. Massive two sweep through two resonances. And on the bump test, we had those two resonances close together. So this is matching exactly on the pump. When it's in there, it's doing that. It's moving on the floor. Here is our under speed, which shows the faster we go, the further we move out from the resonance. So we sat down, we showed them all the data, said, right, well, why is this failing? Why has it not failed before? There are so many different stories about things setting on fire, and he did this, she did that. But basically, a long time ago, they used to run the motors at full speed. They used to just step them up to max speed and let it run. Then the energy efficiency team did some tests, and they worked out it's more energy efficient to run it slower. So all they've done now is, instead of running up through a resonance and they're on the top end of a resonance, and the pump can just take it, the bearings can just take it, they've slowed it down and they've pushed it into a resonance. So now they're running 24/7 at its resonance. And what we got is, well, why is it failing? Well, the motor powered by metal bearing tilting pads are failing because they've got metal to metal contact. Well, that metal to metal contact gives overload fatigue, increased dynamic load on the bearing, and the bearing fails. Well, it's doing that because we have very high directional motion. So imagine the motor here, a massive motor clamped solid down, the top's free to whip about. Then here, coming down, we've got a 6-meter cardinal shaft. So the pivot point, which is taking all the energy, is the drive end tilting pad bearing. So that is inherently due to the structural resonances on the structure, which then you can take it one step further and say is because they change speed and then they're running in the resonance rather than on the peak of the resonance. We thought we did our job and they could understand all that, but unfortunately, because it's been going on for so long, so many people say there's misalignment this, imbalance that. No one actually took a step back and looked at the whole system, that they weren't totally convinced. Well, we concluded no issues with the motor repairers. We did an acceptance test in the workshop, put it on site. That motor is fine. But it's coincidental now that at the running speed, we're getting a structural resonance, which is amplifying the vibration, as increasing the dynamic loads on the drive end bearing. This then is causing the Babbitt fatigue, cracking, and failure. Now, this is about 2017, so we've been going around for a couple of months. And at this time, I was chatting to Keith, RMS, and they were using motion amplification. So this is just actually sort of come in and they're starting to use it and find their feet with it. So I gave Dean a call, got hold of Stu and Keith. Keith came down to site, and with Keith we tested the motor. So I had all my bump test data, all my vibration data. I knew that that motor was twisted. I knew the frequencies it was running at. Now here is a standard video. Let me play this for you. So if you watch this here, this is the fourth floor. You can actually see on the live standard video, you can see where the cable guard there is flapping a little bit. So you got the cable guard flapping, but obviously it's amplified hugely here. But you can see the motor is doing this. It's like trying to oscillate and it's juddering a bit. This is exactly what we were seeing in the VA. And what convinced us about motion amplification being pretty darn good is what Keith measured here was the exact same frequency I was getting with my contact accelerometers. Now this is a bed plate, so this is a fourth floor. So you'll stand on the floor and you think nothing wrong. I have the motor here on a flange and a round tubing, and these like are gussets which hold the round tubing in place. And this is the floor. It starts off as a normal video and it goes into MA. Now you can actually see here, you can see all this flexing, and the motor here is trying to wobble. That's normal with our card moving, and then the motor's doing this, and actually the bed plate is twisting like this. Can you put the camera underneath? So this is the webbing or the gusset. That's the big round flange, motor, and your bed plate. You can see there that bed plate is just twisting. And what was great was that the frequency of motion, what we got of MA, was bob on to the VA. Now, once we had this, we showed the client this. So this is 217. This is like new technology. They accepted that the motor repairer was fine and that the issue was structural on site, coincidentally with when they changed the speeds. That was great. So then we had to work out, well, how do we stop these motor fading? The easiest option would be just to speed the motors back up to the highest set point, because they ran fine at that for years and years. That wasn't an option because energy efficiency is stated they had to run lower. Next would be redesign of the pumping station. Put in instead of a card in the shaft, motor and pump, just put a standalone submersible pump set down below and let that run. Again, that was not viable. This is a really old station. So we suggested stiffening up here, because this is the point it's twisting at. It's the actual round in the gussets, putting a few more gussets in, doing things little by little, no big steps. But unfortunately, the boiler makers got involved and the fabricators, and I was chatting to them and they said, well, this won't bend. They put some massive RSJs under here. So this here, bear in mind, is 2.5 meters long by 40 centimeters high. Two massive RSJs put in, drilled into the walls, bolted up solid. I did say, yep, it may work, but we're more concerned about the flange twisting. We don't want to do these big costly modifications, which could cause more problem. That still could just bend. And they wouldn't have it, this is a big steel, it does not bend. We said, everything in the world will move at a certain frequency. But anyway, the customer decided to go for this, and they put all this huge steelwork in a grey coal scaffold up underneath, and this is what happened. Still high directional vibration, but now 35 millimeters per second. So we have the usual range, and it shot up here, and now the range was huge. It would go up to 35 millimeters per second. Well, they took it out, and then he said, right, well, what can we do? I said, well, there's a million and one things we could try. You could try and put sandbags underneath, bellows with water so the water moves. And I said, well, we could try a dynamic vibration absorber. Now, this is sort of more of a joke because they think it's magic, but really it's just physics. It is what it is. So a DVA, a dynamic vibration absorber, is basically a tune mass spring system where you want to reduce or eliminate some harmonically excited motion. So everything that rotates will induce a vibration. We call it Sod's law. Sod's law is you're going to hit a structural resonance, and usually you can stiffen and shift it up, or add mass or bring it down. But in this case, it's quite a huge, complex one that we said, well, let's try a DVA. So properly installed, they can neutralize your unwanted vibration, which would then cause catastrophic failure. They're different than tune mass dampers. So you think of the Tokyo Tower with a huge ball when the earthquake comes, that's like a tune mass damper. We're doing a dynamic vibration absorber. You might know these from on some suspension bridges. When the cables come down, they got these little wire things. So when the wind hits a certain speed, these will vibrate. And all the power line overhead cables, they're going to be resonant at a certain frequency with wind arrow flutter. But they will have those little dynamic absorbers. And I even think some old cars in the States, they had some exhaust problems, rattling under cars. They have a dynamic vibration absorber to solve it. So I've been looking at these since I did my level 3 back in Australia. And there's a few different methods about the Fox-key method and Dunkley method. And I decided to go for give the Dunkley method. Basically, by knowing the material properties, the Young's modulus, the density of the steel, the distance from the fixing point to where your mass is, you can actually make a piece of item that will self-resonate or excite at a certain frequency. So you think of the opera singer and the glass, she hits a certain frequency, that glass resonates and explodes. So this design we came up with, that was going to be the mounting plate to go on the lifting lug. 2 bits there so we could pivot it and arc it around because we weren't sure what way would be best. And also we had an adapter up here, so we got a bit of range because you can calculate things as much as you like in theory, but in reality, it's usually different. So this is the final design. We put some safety tethers as well at the top because we weren't too sure that when these break, because the whole point of these are designed to absorb energy, transfer energy, and these were fatigue, which would be a lot cheaper than the motor. So we were worried whether they would fly across the room or drop down. So we had a top safety tether, a bottom safety tether. So if they did go, they're not going to go far. And we put 4 of them around here. We tested them. We tested them at different angles. Nothing seemed to change. They seemed to work best the higher they were. This is actually here a video. I'll play that for you. This is a live video. So the motor's running, and these at the top now are self-exciting. So I designed these to be excited at the highest frequency we had on rotational speed. Now they're only good for one frequency. And on this unit, it ran at set point 3 the most, so we tuned it to set point 3 because this is the one they're running at for 24/7, which is causing the fatigue. So as you see here now, at set point 3, they're exciting, and we were going around adjusting them, tweaking them, and they were all sort of interacting with each other, but they seem to be working. This is a slow motion video now. There you go. If you watch that there, if you look here, you can actually see it's bending there. So this is now slow motion just on your mobile phone, and you can see it's bending. So we're expecting over time it to break here, but is it actually working? It looks like it's vibrating, but is it taking the energy which is causing the motor to do this? It was, and it worked really well. So this is a trend of the normal range. Then we had the range when they stiffened up the steelwork, and now we have the range down here with the dynamic vibration absorbers fitted. These are the radio level readings at the top and the bottom. So we went from normal operation at the top, 10.8 to 8.2, went up to 35 and 18 with the steelwork changes, and down to 5.4 and 5.8. And at the driving bottom there, you can see the changes as well. So even in normal operation at the bottom, it's improved a lot. Now, what we've done here is this is a plot of the speed, set point 5 to 0. Green was before the dampers were fitted, and blue was after. We designed it to tune it with speed set point 3, and it worked perfectly. Number 3 was the lowest. But what you will see here, strangely, is number 4 is back up there. Well, that shows you you could design as much as you like in theory, but without putting it to practice and testing it, you don't know what's going to happen. But at set point 3, where she runs all the time, it was the lowest vibration, so we were very, very happy with that. This one here shows you the radial. So what we've done is we ratioed it up. So if it is 0, it means the shaft is dead still. So we don't want this motor to whip and stress the bottom bearing. So under normal operation, we had a ratio of 2.65 at the top. Structural modifications, the top one is a 16.83 and 3.63 at the bottom. With a dynamic vibration absorber, the actual bottom motion is the same, 0.3, but now the top is 0.4. So now that shaft is running nice and sweet. She's rotating really lovely. So it's not whipping at the top, which is going to stress out the bottom bearing. But that was our theory, is that what we're aiming to do is absorb the energy. So we went back after 12 months, and they said to us, one of them's not working. So it's been going for 12 months, hasn't failed yet. So touch wood, we're looking like we are actually doing it. We're absorbing energy, and that the problem was the whipping in the motor was stressing out the bearing, putting too much dynamic load to the bottom bearing. If you look here, a little crack, and we can see signs of fretting. Now the motor was still running when we went on site. This one wasn't working, but it stood dead still. Tethers, safety tethers were still there, but nothing was wrong with it. And then in hindsight, you think about it, we designed it to vibrate at a certain frequency. As soon as that bar cracked, the whole dynamics, the physics of that bar changed. So hence, it stopped vibrating. So it literally just stood there. You could grab that and just pull it off. And you can see there, it is cracked exactly where you would expect it to crack. So we were really chuffed. So the motor had lasted more than a year. This had worked. This has absorbed the energy. Within a 12-month period, it had fatigued and cracked. So then you look at, well, that's great, but we're going to have to put a plan in. So every 10 months, these bars are changed. Now, these bars are a lot cheaper than overall motor, let alone the disruption to the process. And you see here, so we came with one of the arms were broken. We replaced all the arms and got it down to 4.5 millimeters per second. So they're running a lot smoother now. So the summary is, you may think DVAs is a patch, a temporary fix, but you need to look at every single job. You need to stand back and look at it, because yes, we would have liked to rip down a pumping station, build a new pumping station. Pumps were all great, never had a problem. But in this instance, the pumping station was so old, it cost too much, disrupt production, process, the customers. It is not, you just can't do it. So this was the only realistic opportunity to make the assets last longer. The average cost for the bearings is £15,000. And if it wipes out, you're talking 55k for a rewind. You got 4 of these, and they are failing on average every 12, 13 months. So that's 2017 to 2018. We're now 2020, and none of them have failed. And they're regularly changing out these arms. So this shows you that the cost of an arm compared to that, it works out. So we're really chuffed that it's worked, and I'm sure there's lots and lots of other opportunities out there. But a dynamic vibration absorber is a solution, but you mustn't use it where it's fit to use. And this was a perfect situation. So that's case study 6. We'll probably have a break for a bit before we show you some more case studies. But as part of our training in the Reliability Training Institute, I've come across these sayings. Now, I haven't made these sayings up. I've heard these sayings from people. People often say slang and something, and you pick up and think that's really good. And I must say the first 3 on here are the best, because it's the most important part of any program is a person performing a data collection analysis. So if you haven't got a technician, a millwright, a fitter who wants to do it and do it right, just don't bother. The second most important part of any program is a training given to the person selected. We've got lots of new gadgets out there now. All the OEMs will come on and go, Internet of Things this and this, that. Yeah, do it yourself. In reality, it won't. It will help you see the wood for the trees, but training and mentoring is critical. Experience is what you need. And as I say, 5 years of experience is not the same as 5 years of 1 year's experience working on the same plant. So you can pause it, have a look through these. You might recognize some of these. Feel free to say them to people. Thank you very much for listening. As I said, we can help you with problem solving, reliability solutions like this one. If you need some help, someone just come and do a sanity check, we can come and help you. Upskilling your workforce practically, traditional contractor services, and as I said before, I'm using the Mobius training partner since 2004. So we're delivering courses to ISO 18436, and at the end you can have the Mobius MyBox certification or the BINDT certification. On each case studies I show this at the end, I'm trying to hammer home to people, don't only do VA, don't only do lubrication, don't only do thermography or ultrasound. Each tool can be an indicator or predictor of a particular failure mode. And as I said, in my book, we cover that extensively in 2 chapters. So thank you very much for listening. And if you've missed any of the previous case studies, go to the Reliability Maintenance Solutions website, go on to blog, and they'll be there. You get them through LinkedIn, they're available in a few places. Thank you very much.